Welcome back to the London Futurists podcast. In this episode, we're going to look further into the future than usual. We'll explore the fun and games that humanity might get up to in 1,000 years or more, surrounding whole stars with energy harvesting panels, sending easily detectable messages across space which will last until the stars die out. Accompanying us on these fascinating thought experiments is Paul Sutter, a NASA advisor and theoretical cosmologist at the Institute for Advanced Computational Science at Stony Brook University in New York, and a visiting professor at Barnard College, Columbia University, also in New York. He's an award-winning science communicator and TV host. Paul, welcome to the London Futurist podcast.
Oh, thank you so much for having me. This is going to be a very fun conversation.
I'm looking forward to it as well. Thanks, Paul.
So, Paul, since you're going to be our guide in some pretty wild territory, what should our listeners know about your background?
I'm a scientist and a science communicator. I enjoy talking about all the wonderful mysteries that surround us in the universe and also investigating just interesting thought experiments like the ones we are going to engage in today, where it's not necessarily technology that's right around the corner or might not even be possible, but it gives us interesting opportunities to talk about some really, really fun physics.
Now, I was very struck by your recent article about the feasibility of constructing a Dyson sphere. What is a Dyson sphere and what did you conclude about it?
Yeah, so a Dyson sphere is an idea attributed to the great physicist and all-around genius, Freeman Dyson, who was investigating the far future of humanity. We like to think of ourselves as a sophisticated species, that we use a lot of energy, we do a lot of cool things with that energy, and that as time goes on, our energy consumption needs go up. We need more and more resources to do the things that we enjoy doing as a species. We've had great success in extracting energy from our planet, especially in the form of fossil fuels. That great success comes with some dark sides, like the abundance of carbon that we are emitting into our atmosphere with disastrous consequences. So we are turning to alternative sources of energy like wind power, trying to expand hydroelectric power, expanding nuclear power, researching nuclear fusion. We're trying to find new sources of energy to power ourselves. And you can imagine, it's not guaranteed, but you can imagine that far into the future, we're talking 1,000 years, 10,000 years into the future, that our needs, our energy needs for our civilization, for our species, for ourselves, will outstrip anything that we could accomplish here on the surface of the Earth. Where you could imagine coating the entire surface of our planet, which would have disastrous ecological consequences, but this is a thought experiment. You can imagine, let's say, coating the entire surface of our planet in solar panels so that we capture every single bit of energy coming from the sun and hitting the Earth. And we use this energy to do whatever we want, to power computers and industry and spam email accounts and crypto mining and like all the stuff that we use energy for.
In that scenario, I guess we'd go and live underground and the panels would be on top.
Yeah. Like I said, this would be generally a disaster for the Earth, but you could imagine even in this extreme scenario that we are accessing and tapping every single possible amount of energy that is accessible to us on the surface of the Earth. That amount of energy, even if we were to cover the surface of the planet in solar panels, we are capturing an insignificant fraction of all the energy that's available in the entire solar system. Our sun produces so much energy, so much heat, so much light, but most of that light just goes off into empty space beyond the bounds of the solar system, never to be seen again. Only the barest fraction, like 1 part in a billion of the sun's energy, intersects the surface of the Earth. We are tiny compared to the volume of our solar system. So even if we were to imagine coating the surface of the Earth in solar panels, we are barely scratching the surface of the available energy produced by our sun. And then this is the launch point for the thought experiment by Freeman Dyson, which is, what if we were to engage in massive solar system engineering projects to try to capture more energy that's being produced by the sun and try to capture more of it? And so the idea is we have to go off planet to do this. We can't just live on the surface of any one planet, because the surface of any one planet gets only an insignificant fraction of all the sun's output. So we have to make some transformations. We have to pick a planet. It could be the Earth. It could be Mercury. It could be Jupiter. Pick any planet you want and blow it up, transform it, take it apart piece by piece, and then reassemble it, that planet, into a giant shell that surrounds the sun and captures more of that solar energy. And because the sun is putting out 1 billion times more energy than we could ever capture on the surface of one planet, this means that if we engage in this giant mega engineering project, we could capture 1 billion times more energy than we could ever imagine having available on the surface of a planet. The side benefit of this giant engineering project is that we would have so much more surface area available for us to live our lives. So if you imagine a future where the human population continues to grow, this puts a lot of stress on our ecological systems, our climate systems, and we start fighting over resources, we start fighting over land because there isn't enough of the good spots for all of us. So we fight over those good spots. But you can imagine if you were to essentially turn a planet inside out and deconstruct it and build a shell, you get to live on the inside of that shell, enjoying sunlight. And also the amount of land available to you goes up by a factor of 10,000.
And also, if you did that, you could have the Earth revert pretty much to a state of nature. So humans could live and do all our manufacturing activities on the shell of this Dyson sphere. And the Earth could be just reverted to what it was a few hundred years ago. Jeff Bezos was suggesting this on a podcast recently. I think it's a great idea. Get industry off the planet. Because the Earth is the only planet that we know that is beautiful as the one we have.
Oh, yes. Earth is very pretty and very special and very unique and very fragile. And I do think the future of humanity lies in putting heavy industry out into space. There are a lot of challenges associated with that, but humanity is used to dealing with significant challenges and we can overcome them. The idea of a Dyson sphere goes one step beyond. You're absolutely right. We could preserve the Earth. We could move off the Earth, leave it in a pristine state, as long as the Earth sits inside of the Dyson sphere. Because if you put a Dyson sphere around a star, you are covering up all the light of the star and blocking the light of that star. And so if the Dyson sphere were inside the orbit of the Earth would not get any sunlight at all, which would kind of be bad, especially if our goal is trying to preserve life on Earth.
We'll be right back after a quick break.
In today's fast-paced tech world, finding the right talent is more challenging than ever. That's where EcoGlobal.tech steps in. Whether you're a startup or a large enterprise, EcoGlobal specializes in connecting you with the top-tier remote IT professionals from Eastern Europe. To give you peace of mind that you're hiring the right professional, they offer 2-week money-back guarantee on top of their 3-month probation period. So, if you're looking to boost your tech team with a minimum risk and drive your projects forward, visit EcoGlobal.tech today and book a free consultation. That's ECHOGlobal.tech. Mention Echo Podcast and get an additional 7% discount.
Paul, let's take a mini step into that future which you described. I think you said it might be something like 1,000 years' time. Who knows? But what about 10 or 20 years' time when people are saying not do a whole Dyson sphere, but put lots of space-based solar energy collectors into orbit around the Earth so that we could get access to a larger fraction of the sunlight that's coming in the general direction of the Earth? Is that something that's part of your vision for the future?
This is something that is possible. In the short term, in that 10 to 20 year time frame, getting into space is enormously expensive. One of the most complicated things that humanity ever does is launch something into space. And yeah, we launch solar panels into space all the time. We use them to power our satellites and our space stations and our spaceships. And we're really good at collecting light in space. We even have a probe around the planet Jupiter, the Juno probe, that is powered entirely by these like giant solar arrays, the largest solar arrays sent to the outer solar system. We're really good at that, and we've developed a lot of great technologies for that. And there are even some advanced technologies, some stuff on the drawing board to have even larger solar panels that fold up and then deploy after launch, so you could have much larger collecting areas so you can capture a lot of energy. The challenge was using that as a power plant, so to speak, is getting that energy back onto the Earth. And there are some interesting experiments and ideas along this direction of collecting solar radiation, converting it to energy, and then beaming down, say, microwave radiation, which is then collected on the surface of the Earth. This is a very intriguing idea. For the next 10 or 20 years, it's always going to be cheaper to simply build more solar panels out in the desert or somewhere on the surface of the Earth, because then you avoid all the problems associated with launch costs and deployment.
Yeah. So going back to the Dyson sphere, your article took a kind of first principles approach to working out whether it could ever be economically sensible. What did you conclude?
Yeah, so I approached this problem not as an engineer, because I'm not an engineer, but as a physicist and just looking at energy. Because it sounds like fun, and it is, to dismantle a planet and turn it into a giant shell surrounding a star. But there's a cost to that. If you want to disassemble a planet, you're going to have to put some sweat into it. This is going to cost you some energy. In fact, it's going to have to cost you a lot of energy. And we can actually calculate the energy required to dismantle a planet. In physics, we call this the binding energy. You have to put in at least that amount of energy in order to pull all the pieces of a planet apart. And then you reassemble it into solar panels. Then you start collecting energy. From my calculations, what I did was look at how long will it take to pay back your investment. If you have to invest a certain amount of energy to transform a planet into a Dyson sphere, how long will it take you till you get that energy back? And the answers are all over the place. I made some simplifying assumptions. I assumed that all of the mass of a planet is available for building a solar panel. Solar panels actually require a lot of rare elements and hard to find elements. So you can't just like scoop up a mountain and turn it into a mountain-sized solar panel. There are some intricacies involved, but I just assumed that we could do it. So this is like best case scenario kind of stuff. And the answer really depends on how thick your shell is. Because if you make a really, really thick shell, then you end up not being able to cover as much of a sphere surrounding your star. So you don't get to capture as much of that radiation. And if you're able to get away with a very thin shell, then you can have a bigger surface area. You can have a bigger shell surrounding your star. You can capture a greater fraction of its output. In my calculations, I played around with anywhere from a meter thick to a kilometer thick, just to explore this. And also we have to talk about efficiency, because solar panels aren't 100% efficient. Not all of the energy that hits a solar panel actually gets converted into useful electricity. There's always waste. There's always inefficiencies. So you can't have anything 100%. So also in my calculations, I varied things from an efficiency of 10% to an efficiency of 90%. Again, just to explore the bounds. And what I found was that on the low side, on the most pessimistic side, it would take approximately 60,000 years to pay back the energy cost of unbinding a planet and ripping it apart and turning it into solar panels.
Well, that's not going to get you VC money.
Yeah, that's a pretty long time horizon. Although if we're contemplating thousands of years in the future and we're capable of these engineering projects, maybe a VC of the future will say, 60,000 years, not so bad. I'll take a bet on that. But that was the worst case scenario. And this is disassembling the Earth. We can talk about other planets later. If we disassemble the Earth and we turn it into kilometer thick panels at 10% efficiency, the worst case scenario, the payback time is about 60,000 years. If we're much more efficient, if our panels are 90% efficient and the panels are only 1 meter thick, then the payback time collapses to just a handful of years.
Does it change if you disassemble something much smaller? You might try this experiment first on an asteroid, or perhaps one of the unfortunate moons of Mars.
Absolutely. So this calculation does depend on the mass of the object you're working with, because the smaller the object, the easier it is to disassemble. But on the other side, the less stuff you have available to turn into solar panels. So we can look at something, say, like Mercury. Mercury, it's smaller, so it has that advantage. It's easier to rip apart, and it's much closer to the sun. So you don't need as big of a shell in order to capture more and more light. Again, with these bounds, if we take something like Mercury and we have kilometer thick panels and we have 10% efficiency, then the payback time is around 1,000 years, much, much better than dealing with the Earth.
And would it be possible to disassemble Mercury and to reassemble it as solar panels around the sun, but leave a space in the middle so that the light that was arriving on the Earth previously is still arriving, the same amount of it? Would that be feasible?
Oh, yes. In fact, this would be necessary because in Freeman Dyson's original calculations, which he did back in the 60s, back of the envelope, bare bones calculations, just interesting idea. He talked about building a complete shell. But it turns out that a completed, fixed, rigid shell is enormously unstable. That you have to keep the sun in the exact center of that shell for everything to balance out. Otherwise, gravitational stresses just tear it apart. And that's a highly unstable, highly unbalanced situation. So you're never going to get it to work. So instead of a shell, we envision what's called a Dyson swarm, which is a series of panels, each one free floating, each one big, as big as you want, like 100 miles across, 1,000 miles across, but each one free floating independently in its own orbit. And so if we were to tear apart Mercury and actually engage in this, we would want a set of free floating panels. And then we would want to make sure that there is a gap in those panels that allows light to always reach the Earth.
That would be a nice thing to do for us all. Back in 1964, there was a Soviet astronomer, Nikolai Kardashev, who proposed a scale to measure a civilization's level of technological advancement based on the amount of energy it's capable of using. And this discussion is taking us right into that. So a Type 1 civilization is one that can access all the energy available on its own planet. And in our case, that would be something like 2 times 10 to the 17 watts, which is 4 orders of magnitude above our current energy access, 2 times 10 to the 13 watts. And then a Type 2 Kardashev civilization consumes a whole star's energy. So they built a Dyson sphere, or a Dyson swarm. And that would give them 4 times 10 to the 26 watts. So going up from 10 to the 17 to 10 to the 26, which is an awful lot. And then there's a Type 3 Kardashev civilization, which captures all the energy emitted by its galaxy, 4 times 10 to the 37 watts. And it's always struck me that we don't see any galactic engineering on the scale of Type 2 or Type 3 civilizations going on. We've not been looking at the stars with really good instruments for very long, but we have looked at a lot. And there's no apparent evidence of anybody swinging stars around, breaking them up, or shrouding them in swarms, or swinging galaxies around. Which makes me wonder whether this is some kind of evidence that the answer to the Fermi question, where is everybody? Are there any aliens in the universe? Is no. Do you think that's decent evidence for that argument?
You make an excellent point, which has been noted by astronomers, which is If an alien civilization built a Dyson sphere, we could potentially see it because they would completely cover up their star or a good fraction of their star. And what would happen to the light from that star, because the light from that star would hit the solar panels on the inner surface, get converted into electricity, it'd be used for work, they do whatever they want. But then energy can't be created or destroyed. It can only be transformed, and that energy has to go somewhere. And it would be left in the form of heat, excess heat on the outer side of that shell. And things that are very hot would tend to glow in the infrared regime of the electromagnetic spectrum. So if we were to see a star that kind of looked like a star, but was much bigger and much fuzzier and way, way, way at the wrong wavelength of light, that might be a sign that that is actually a Dyson sphere surrounding a star. There was a big kerfuffle a few years ago when astronomers with the Kepler Space Telescope, Kepler is a telescope looking for planets orbiting other stars, they found variations in brightness from a particular star that did not fit the expected behavior of an orbiting planet. And they announced that maybe they had found what they called a megastructure, like Dyson panels or a Dyson swarm. And like these giant panels were floating in front of the face of the star, dimming the light that we would see. And then the panel would move off in its orbit and the star would return to its normal brightness. It turns out that was just dust. It was just a ring of dust surrounding that star, not a megastructure. But we have searched for Dyson spheres in our local galaxy for any signs of Dyson spheres. We've looked at other galaxies looking for these type 3 civilizations that would start one by one shifting their stars to become Dyson spheres so that they can capture as much energy as possible. This would change the overall appearance of the galaxy. We've searched millions of galaxies and come up empty. We've searched millions of stars and come up empty. And so the conclusions, it's not just one firm conclusion. One conclusion is intelligent life is exceedingly rare, and everywhere we've looked, we haven't found anybody because there's no one to find. Another conclusion is that there are intelligent species out there, but for some reason, Dyson spheres don't work out. There is some understanding of physics that we're missing that prevents Dyson spheres from being created. And then the last conclusion that you could possibly reach is that Dyson spheres are possible, just no one bothers to do it because maybe it's kind of a stupid idea.
It's been suggested that in the future, intelligent life might get by on much less energy rather than requiring more energy. One of the trends we can see is that some things are more efficient than before. And in the future, perhaps we'll be content to live our lives in wonderful virtual worlds on the microscale or nanoscale.
Exactly. There's this bias of presentism where we've seen over the past 100 years this rapid increase in the use of energy and explosive growth in technological sophistication. And there is a bias that we can have that this kind of progression will continue into the future and that we'll always need more and more resources and we'll always need more and more energy. That's not necessarily true. The human population right now is far less than what we predicted it would be back in the 1990s or 1980s. The human population growth rate is slowing. There aren't necessarily going to be 1 trillion human beings living in 1,000 years. That's not necessarily the case. And you're absolutely right. We can find more efficient ways to use energy or put our energy into different things. The stuff we care about now in 2024 may not be the kinds of things we care about in 3024. And then if you do need a lot of energy, maybe resculpting your solar system, that takes a lot of work. You need a lot of rare elements. It's a major headache. Maybe it's more energetically efficient to just find the nearest black hole or neutron star and set up shop around that and suck energy out of those.
And do you have any view as to which of these various possibilities are most likely? Do you think there may well be other intelligences out there in which they've had their own Freeman Dyson and Paul Sutter, and they've ended up with Dyson spheres which are invisible to us for whatever reason? Is that a possibility you put highly on your probability scale?
I honestly don't know. That's one of the best things about the future is you don't know what you're going to get.
Yeah.
Now, you talked at the beginning about wonderful scientific mysteries of the universe. I wonder if I can tempt you to mention any other things that you believe are profound and fascinating mysteries about the universe we inhabit.
Oh, this is my day job. This is my bread and butter. What gets me up in the morning are those profound mysteries about the universe that we live in. We are surrounded by mysteries. We've learned a lot about our universe, but it seems like every time we answer one question, a dozen more come up in its wake, which is the beauty of this exploration through science of our universe. One of the most enduring mysteries that we're facing is the ultimate fate of the universe. We don't understand the fundamental ingredients of the universe. We thought we had a lock on it. We thought we understood stars and galaxies and dust clouds and matter. And it turns out that the kind of stuff that we are made of, protons and neutrons and electrons, makes up less than 5% of all the stuff in the universe. And we've only come to this realization in this generation, and we're still grappling with it. Most of the universe is made of substances that we call dark matter and dark energy, but those are just placeholder names for stuff that we fundamentally don't understand. And so it's a delight to investigate this dark side of our universe, this invisible and hidden side of our universe that turns out to be the most important part.
Alternatives to dark matter and dark energy are that maybe we got the theories of gravity wrong. We loved Newton's theories for hundreds of years, then we've loved Einstein's theories, but perhaps rather than there being more matter, there's just a more complicated or maybe a more profoundly interesting way of gravity operating that we haven't understood yet.
Oh, absolutely. That is always an option. The trouble with these theories of modified gravity, and many of them, many versions have been proposed, is that they kind of don't work. If you look at a galaxy and the motions of stars within galaxies aren't adding up, there has to be more stuff. And you say, well, hold on. Maybe instead of adding more stuff into this galaxy, this invisible form of matter called dark matter, maybe we just need a modified version of Newtonian physics or general relativity to explain what's going on. And that's fine. But then you take that and then you look at a galaxy cluster, a much larger structure, and you say, well, we need more stuff to explain the motions of galaxies inside of this cluster. Dark matter can account for that. The presence of an invisible form of matter can account for that, but the theories of modified gravity can't. And then you look at the early universe. We have this beautiful data set called the cosmic microwave background. This is leftover light from when our universe was only 380,000 years old. We can observe it all around the sky today. And you look at the properties of the cosmic microwave background and you say, oh, there needs to be stuff in here that does not interact with light, does not interact with normal matter. There has to be a massive component that's dark. There's no theory of modified gravity that can explain the properties that we see in the cosmic microwave background. That's why the vast majority of astronomers believe that there is something like dark matter out in the universe, because the dark matter hypothesis is able to explain a vast wealth of data with a very simple and straightforward hypothesis, whereas the modified gravity proposals always come up short and always fall short once you start looking at more than one data set, which we must as scientists.
And what are the latest explanations or theories for what dark matter and dark energy might actually be?
Our best guess with dark matter is that it is some kind of particle that we currently do not understand that does not interact with light and it does not interact with matter, at least very often. Because if it did interact with light and normal matter very often, we would see it. We would have detected it by now. So as to be largely invisible, present since the earliest days of the universe, just like all the other stuff in the cosmos, but just interacts through gravity. It gravitationally attracts, it binds together, and it provides the glue, the backbone for galaxies and clusters and all the large structures in our universe. We do not know the identity of that particle. Many of our simplest ideas of what that particle could be actually have been ruled out by experiments. but we're continuing to search for what that identity is. Dark energy, we're lost. We've got no clue. We think it has something to do with the fundamental vacuum energy of space-time itself, but all of our naive calculations about what this could be and how much there should be in the universe are way off, like 120 orders of magnitude off. So the naive calculations aren't even bringing us close to the answer, and sophisticated approaches aren't making much more headway either. Dark energy is a true enduring mystery.
What do you say to people who respond to all of this with the idea, well, science isn't anything like as good as was made out to be in the past? When I was at university, people were very excited about superstrings. There was this smart guy called Edward Witten who had done this incredible piece of mathematics, and it was just going to be a few years perhaps before we got it all sorted out. And inflation, the theory of how the universe expanded very quickly at the beginning, again, it seemed quite attractive that this is almost solved. But as far as I can see, there's no satisfactory solutions in place, and I do notice your new book is called Rescue in Science. This may be something different, but it does suggest that there might be something wrong with the herd mentality of some scientists, perhaps.
There are issues with herd mentality and fads and fashion in science like any other human enterprise. Superstring theory was a really solid idea, and now it seems it's experimentally on very, very shaky ground. In fact, large portions of versions of string theory, superstring theory, have been ruled out by lack of evidence. And you know what? It's fine to chase an idea that seems good, and then we let nature be the ultimate arbiter, and then we have to change our minds. When it comes to inflation theory, we are at much more solid ground. I've personally done a lot of work with inflation theory. Inflation theory is a theory of the extremely early moments of the Big Bang. We do not understand large parts of this event, but all the evidence indicates that something like this event did occur because we have no other way of explaining how our universe got its spots, so to speak, how it got to have galaxies and large structures arise in the first place. Inflation theory is our only approach that gets the statistics right. So something like inflation seems to have happened in the early universe, but we're still working on what exactly that event was. This is pushing the boundaries of physics, so of course there are a lot of unknowns, because that is always the definition of the boundary of physics. I do encounter people, like you just pointed out, that like, hey, there were all these promises made that were right around the corner. I put the fault on that on the people who were promoting these ideas and saying that the answer is right around the corner. I remember reading Brian Greene's book in the late 90s, early 2000s about the superstring revolution, and it did feel like any minute now we would crack it, and that was a quarter century ago, and we haven't cracked it. That's the fault of people like Ed Witten and Brian Greene who are saying, oh, don't worry, we're going to figure out superstring theory like any minute now. You can't make those kinds of promises in science because you never know how long it's going to take to come to an understanding, to get new data, to have the theoretical insight that will make sense. You never know. And so you can't say it's right around the corner. The example I like to point to is that it took us over a century to decide that atoms existed. The chemist Dalton first proposed the idea of atomic elements were actually atoms in the early 1800s, and the idea wasn't confirmed until the early 1900s with some of the work by Albert Einstein, actually. It took us 100 years to decide that atoms existed. So science is slow, science is patient, science is contentious, and there are always 99 blind alleys for every correct answer. And we have to keep chipping away, and it is much slower than people appreciate.
And I guess it would be pretty boring if we had all the answers. It's much more fun if there's many puzzles to go after.
Yeah, and I'd be out of a job, which would be really horrible.
We can't have that. We can't have that. But we are running out of time. So I want to wind up by asking you an unfair question, Paul. What odds would you give us as humanity of surviving long enough to get to be a type 1 Kardashev civilization? In other words, able to use all of the energy that lands on this planet.
I don't know if we'll ever achieve type 1. I don't know if this Kardashev scale is a useful classification for projecting the future of a civilization. I feel like that constrains our options. It constrains our choices. We have actually a much richer and much more diverse future ahead of us than the Kardashev scale might imply. Because the implication is that, if you don't reach type 1, you're some sort of an inferior species. No, we get to decide, especially because we're the only intelligent species that we know of in the universe. We get to decide what sophistication looks like. We get to decide what our own future looks like. Maybe it looks like consuming as much energy as possible. Maybe it doesn't. I think humanity will survive. We have survived as a species for approximately, 200,000 years? And yeah, we're going to face some challenges like nuclear weapons, like climate change, and who knows what else in the coming centuries. We will have to navigate those challenges, but we're survivors. We're a hardy species. We're a clever species. I think we will continue far, far into the future. And my only goal, my only hope is that our descendants look back on what we have accomplished and look back at that with pride.
How important is the role of science, and indeed science communication, in helping us to reach that better outcome? Because I'm reminded of the words of another distinguished science communicator, Carl Sagan, in his book The Demon-Haunted World, where he lamented the potential future, which is now really, in which there's much less respect for science, in which there's much more focus on irrationality, and we might call it post-truth. So do you foresee a potential resurgence of a respect and understanding of science, or are you worried that we might end up in, indeed, a demon-haunted worldview?
I do worry about the declining trust and respect of science, and that is why I wrote my most recent book, Rescuing Science, Restoring Trust in an Age of Doubt. I don't think we're in that bad of a place. I want to put things in context. There was a time when we were burning scientists at the stake, and we don't do that anymore. And so I will take mild disrespect over being burned at the stake anytime. So as a civilization, we're treating scientists much better than we used to. So I will take that. Irrationality, faith, non-scientific worldviews are always going to be a part of the world. I do not see this as a contest, as science versus anything else, because that's insane. I am a scientist. The vast majority of decisions that I make on a daily basis do not involve the scientific method. When I want to decide what to cook for dinner, or who to fall in love with, or any of the innumerable decisions that I make, I'm not making those decisions based on the scientific method. So to try to enforce the scientific method as the only way to approach knowledge, the only way to approach decision making, is foolish and very prideful. Instead, what I seek is that science is a component of people's lives, that people see the value of science, even if they don't employ the scientific method every day in their everyday life, that science is a part of the conversation, that the scientific voice is present in the public sphere and may not always be agreed with, may not always be the determining factor in any kind of societal decision, but is at least respected and at least heard. That is my goal for science, and that is what I place, the responsibility I place on myself, on my fellow scientists, and any science communicators and fans of science, is not to demand that science is the answer, but to show the value of a scientific worldview and to show how powerful and vital that worldview can be.
Well, that's a very reasonable and measured appeal. And I, for one, am very glad that you and your colleagues are not being burnt at the stake anymore. Thank you for sharing your optimism. Let's hope you're right and that humanity has got a great future for many millennia to come. Paul, thank you very much indeed for joining us on the London Futurists podcast.
Thank you so much. It was a pleasure having this conversation.